Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide. To Chapter 2.3, Connecting Differentiability and Continuity. Now, we know a function is continuous over an interval if it's just visually connected. Now, it's not a very formal definition. We've done that in previous videos, but really the idea of connectivity is good enough for continuous if we're looking at a function. Right? We look at this graph right here. There's a hole, not connected, so it's not continuous. We look at another type of graph here. Oh, there's an asymptote, not connected, so it's not continuous. One other option would be, oh, I've got another graph, but here it's got a jump in it, so it's not connected and hence not continuous there either. So it's easy to tell when a graph visually is not connected and hence not continuous. Recall that for continuity, we need a few things to happen. We need the limit to exist at a point, so the limit as x approaches a has to equal f of a, and we need f of a to exist. Essentially, the two sides of the function need to meet. There needs to be a point where they meet, and they all need to agree on that point. And if this happens for every point on an entire interval, we say a function is continuous over that interval. This idea is going to come in handy when we talk about differentiability too. We say that a function is differentiable if two things. F of x is continuous. We just talked about that. And we also need f prime of x to be continuous on the specific interval in question. So what's that mean for us? Just like for continuity, for differentiability, now we're going to need the limit as x approaches a of f prime of x to equal f prime of a, and we need f prime of a to exist, just like we did for continuity. Right? Now this could manifest itself in a couple different ways. In a graph, we can't have any cusps or corners. So what's that look like? Here's an example. This graph has a very dramatic change in direction at that little cusp or corner. We can see the slope changes dramatically from very positive to very negative at that point. Meaning that first part, the limit as x approaches a of f prime of x, that's not even going to exist here because the left limit and the right limit, the slope on the left and the slope on the right at that point, are going to be dramatically different. Another characteristic to look out for is that differentiable functions have no vertical tangents. So if you have a function and you're looking at the graph and you see that it might have a vertical tangent, now what would that look like? Take a look here, see where this graph bends and goes straight up. You can see that little tangent line looks like it's vertical, which means its slope is undefined here, which means the derivative is undefined here, which means f prime of a would not exist, meaning our function is not differentiable at that point. Those are the main two things to look out for. And now, looking up at our definition, see how a differentiable function must also be continuous? This brings us to an important conclusion, that if we have a differentiable function on a certain interval, we also know that function is continuous on that interval as well. Problem is, lots of students make this mistake and flip-flop this idea. It is not always true that a continuous function will be differentiable. So the reverse of this statement is not true. And we can actually see it pretty clearly in the example just to the left, this cusp and corner example. Take a look. Certainly this graph is connected there, so it's continuous, but we already said it's not differentiable because the slopes change dramatically at that point, meaning that the derivative is not continuous there. Let's take a look at a quick example. From what we talked about so far, we can equate the idea of continuity to the idea of being connected. I also like to equate the idea of differentiability to the idea of being smooth. If my graph is smooth and connected, it's differentiable. We can usually get away with that thought, but we also have to be careful and make sure that our derivative exists at the point. But most of the time, smooth and connected is just fine. So let's take a look at this graph of f of x and determine all the values of x where my function is not continuous and where it's not differentiable. If we Follow along our curve to x equals 1. We see the little hole. That's not continuous. We keep tracking along to see the next place where our function's not connected, and that happens over here at x equals 6, where we have this big jump. So not continuous at x equals 6. And just past 6 at this vertical asymptote, we can see our function's definitely not continuous at x equals 7 either. So those are the 3 places where my function's not continuous. But where is it not differentiable? So we're looking for where our function is smooth, where the derivative exists, but it also has to be connected. So the first easy part is, hey, this hole, my function's not connected, and my function's not continuous. It's impossible for my function to be differentiable. So my function's not continuous at x equals 1, so it's not differentiable at x equals 1, 6, or 7. So we might as well add those to the list right now. But are there any other places along this graph where it's not smooth, where the derivative doesn't exist? Yeah, right here at x equals 2, I can see that my graph has a cusp here, and my derivative can't exist here because derivative's talking about slope of the tangent line. And look, there's a tangent line, there's a tangent line, there's a tangent line. All these tangent lines have different slopes. How could I characterize a slope at this point when there are so many different tangent lines? Hence, we say the derivative doesn't exist there. So, not differentiable at x equals 2. And a little bit further along this curve, you see right about here, it looks like we're going a bit vertical. So if we imagined a tangent line at that point, you can see that we could draw a vertical tangent line, which means the slope of a vertical line is undefined. So it looks like we're not differentiable at x equals 4 either. And that's it. Continuous functions need to be connected. Differentiable functions need to be smooth, connected, and the derivative has to exist at the point in question. Now I usually just think about smooth and connected, and most of the time you'll be safe just with those thoughts. Be sure to check out our next video, which helps us find derivatives with our first shortcut, the power rule. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.